name is Abigail, and today I'm going to be talking about my Physics Lab 4 on magnetic braking with Faraday, or Faraday's Law. Today's lab, the purpose is to compare both observational data that we collect through an experiment and computational data that will calculate the time it takes for a bar magnet to fall through an aluminum tube. So today's physics principles are Faraday's Law is the main one. Of course, you could tell that from the title, Braking with Faraday. These are both of the equations with that, the di over dt calculated here, and then the di over dt is also equal to EMF, which is equal to I times R. So that means I is equal to d over dt divided by R. And then we'll also be looking at magnetic dipoles, specifically on-axis dipoles, and this is the formula for that. And I've also included the force formulas. Net force formula for today, F gravity plus F of B, and then F of B is equal to I times delta L cross B. And then also I want to mention that you will see later Newton's second law is going to be used with both the position update and velocity update formulas. And just to preview the results, the experiment average time is 0.654 seconds and the computational time is 0.652 seconds, which are very close, but I will say there could still be some errors in both. So for the experiment, here's my trials. I did 5 trials and you could see the times vary, between 0.56 seconds being the lowest and 0.74 seconds being the greatest time it took, and then the average being 0.654. And just to explain, this data is from actually dropping a bar magnet through the aluminum tube in my living room. So there could be some human error in the calculations of these. It could be closer. I'm pretty sure that probably the 0.74 and 0.56 are a little bit off considering the other 3 are so close together. I just got lucky in having one large outlier and one smaller outlier, which still helped me keep my average time around the same. So for the computational model, I've also included the code in the description because some of this is a little bit small. But the top 2, top left and top right, are initial conditions like mass, the magnitude of mu, the L, width, inner radius, and the full radius. The middle left is the same code I used in lab 3 to find the magnetic field. And then the middle right is calculating di over dt. Yeah, the flux, df over dt, sorry. Sorry, it's a little bit hard for me to see, but yeah. Calculating flux and of the analytic. So you put in the magnet in the ring, find ring of radius, magnet position minus ring position is distance, you find speed, numerator, denominator, divide them, then you get it returned. Bottom left is you end up finding the magnetic force on the magnet, the magnitude of the force on the magnet. And then bottom right, you find the force, the net force, and then you find, like I was talking about earlier, you use Newton's second law to find the bar velocity and the bar position. There's a storm in the background, sorry. So what ifs? Before I get to the what ifs, I just want to mention that on the right is what my computational data looks like after you run the code, which you can run for yourself if you'd like. But the top, you could see the graph, and then the bottom is what the tube with the magnet in it looks like at the end. So what if? What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the following magnet change? So the magnet is going to fall slower because the decrease in resistance leads to an increase in current, which leads to a greater magnetic force, and that greater magnetic force is going to cause the magnet to fall slower. And what if there are holes or slots? What does that do? Well, it's going to cause the opposite effect. The current is going to decrease due to these holes, causing the magnet to fall faster because the magnetic force, because of that current decreasing, the magnetic force is also going to decrease. So thank you for watching my Lab 4 Final Physics Lab.